Assalamualaikum and a very good afternoon to all. So that welcome again to KNC 2113 Thermodynamics 2 class. Okay, right? So today will be your lecture 4 on chemical reactions equilibria. Okay, the objective of this lecture will be to determine the effect of temperature, pressure, and initial compositions on the equilibrium compositions of chemical reactions. And also to introduce you to, I think you know already, the stoichiometric and also the reaction equilibriums for chemical reactions. And also to introduce the equilibrium constants and its temperature dependence and evaluations. And also to develop connection between equilibriums, constant and compositions, and as well as to illustrate the equilibrium conversions for single reactions, consideration of the phase rule and also multi-reaction equilibriums. And lastly will be on fuel cell. Okay, right. So in the general chemical reactions, okay, so we can denote it into this, okay, right? So this is the new here, new one, A1. Okay, this new is called as stoichiometric coefficients, and A stands for the chemical formulas. Okay, right? So for the products, which is on the right side of the chemical reactions equations, is positive. Okay, right? On the negative side, we assume it to be negative for reactants. Okay, for example, for methane react with water here to produce carbon monoxide and hydrogens. Then we can see that the stoichiometric numbers or mu for methane is -1 because it's a reactant. Water also -1. Carbon monoxide is 1 and hydrogen is 3. Okay, right? So we can see that, so if we cut it all into half or 0.5 mole of methane, then we need half mole of water, in which we produce half mole of carbon monoxide and 1.5 mole of hydrogens. Okay, so from this we can see that this ratio here, the change number of mole to the stoichiometric number is the same, right, for both. Okay, for this is for the reactant and this for the products. And we notice it is all the same for both reactant and the products. And then this ratio, we call it as D epsilon. Okay, what is D epsilon? Okay, later, okay, we will define that, okay? Okay, which is the equilibrium coordinates, okay? So in general, this relationship between the change in number of mole and equilibrium constant here, I'm sorry, reaction coordinates here is denoted by D and I equal to nu I D epsilon. Okay, right? And then for a number of a mole number exists, okay, right? So we can integrate this, okay, right? From for this number of mole, integrate from Ni naught to Ni, and then this nu I from 0 to epsilon. Okay, right? So we will got this n minus n naught here because this is only one here, right? And then for this, because this is a constant, then mu I epsilon. Okay, right? So the delta missing. So this is the basic equation for a single species. Okay, right? So the overall sum for n, we got it from this form here. N, summation of n I naught plus epsilon mu I. Okay, right? And then where this is n equal to this and not equal to this, and mu is equal to this. Overall, for the mole fraction of y after species present related to epsilon is this. Okay, right? N1 over n. Okay, this is for vapor, isn't it? That y. So this is the ratio. This is for the pure species, and this for the overall. Okay, right. So when two or more independent reaction proceed simultaneously, substitution J serve as reaction index. Okay, right. So if we have more then one reaction. So we can denote it as J. So the equation again, you can see here, right, is summation of J, right? Vij d epsilon J. Okay, right? So we, right here, we maintain J into constant. So from the integration, there Ni equal to Ni naught and epsilon J equal to 0. They'll provide us with this equation here. So this is very much similar to the previous equation, right? And then you apply it again to the same equations previous, you treat it similarly like in previous equation, and then we got something like this. So it's noticed it is very similar to this, right? Except we have the summation of J. Okay, right? Okay, right. So it shows that the total Gibbs energy of a closed system at constant temperature and pressure must decrease during an irreversible process, and that the condition of equilibrium is reached when G total attain its minimum value. Okay, or the change of Gibbs total energy at constant temperature and pressure should be 0. If you remember from the mathematics, right? If you take the, okay, this is a function. Okay, right? So if let's say you take the differentiations of the function, then you will get a slope. So I will go straight right to this graph here. Okay, so what does it mean here? Okay, this is the epsilon. Okay, right? This is where the stoichiometric equilibrium occur. Okay, right? E, remember E, reaction coordinate when it is in equilibrium, right? So if is it, like for example, from this part here, okay, right? Delta G is positive, right? Positive. I'm sorry, very high. Okay, right? So it tend to reduce until it become to the lowest where it reach equilibrium. Okay, so think of this way. If let's say you have more, okay, on the right side you have more of the reactant and then less of the product. So what the reaction will do is that it will try to make itself in equilibrium. So the reactant will react to produce more products. That's what it means by this reaction. So until it becomes equilibriums. So when we mean by equilibrium, okay, if there are more products than the reactant, so what we will do is that the products will react to produce more reactant. So it go into to the left. That reaction go to the left. Okay, right? So until it become equilibrium. So remember I told you when we talk about equilibrium means that the reactions still occur, right? From reactant to products and products to reactant. But the rate of reactions are the same, constant. Okay, there's no changes. That is equilibrium. Okay, this is further define what is equilibriums. Okay, so that for the equilibriums, okay, I already explained it to you. The total Gibbs energy is it's at the minimum, and its differential is 0, means that whatever direction, it's the same. So toward the end, it's 0. Okay, so if we apply the previous equation in chapter 11, previous lecture, with G, V, S, and species chemical potential, I'm sorry. Okay, right? So we can this, and then we can replace D and I with nu I d epsilon here. Okay, so we can replace this with this, and then we got this equation here, right? Okay. All right. So at constant temperature and pressure, what will happen to this equation? Delta P will be 0. Delta T also will be 0 at constant pressure and temperature. So you will get D and G equal to this. Right? This is what they show here at constant temperature and pressure. Okay, right? And since E is in equilibrium, what does it mean? Delta G here should be what? 0, right? Delta G should be 0. The change here. Remember this graph here, the slope is 0, is horizontal. So this again will be 0 at equilibrium. So you got that? You know, the summation of stoichiometric coefficients, which is I, to chemical potential I, it should equal to 0. Okay, right? So means that the reaction process have achieved equilibriums. Okay, right. So for the in terms of fugacity, we have seen this equation before, okay, right? And then for the Gibbs energy as standard, okay, the dot here, okay, right? The asterisk here, subscript of not here means it as standard condition. Okay, I will call it as not. Okay, right? Can be in this form here, and then we take the difference between the two, and then we got this equation. So this is not new. Okay, right? But combining equation 13.8 and 13.9, okay, some magics of mathematics, and then we got this equation here, this equation, or this equation here. Okay, so what does this mean, the equation? Okay, so this mean is the sum. Okay, right? The sum, the products, the sum of the products, right, of this fugacity in the solution to the standard and stoichiometric coefficients. Okay, and this value, this is what we call as K. Okay, so what is K? K is equilibrium constants. Okay, equilibrium constant. And then this K can be further defined as this, okay, exponent negative delta G naught RT, or ln K equal to negative delta G naught over RT. Okay, you guys will study this more in detail in reaction class later. And so you proceed to your I'm not sure whether it's second year or third year, but I think somewhere in third year in this class. Okay, so by definition also, delta G, we can simplify it to be equal to this, okay, right? The summation of stoichiometric coefficients I and Gibbs energy at standard conditions. Okay. Okay, this is what I mean. In spite of it, dependence on temperature. Okay, right. So this process depends on the temperature. K is called equilibrium constant for reaction. This represented by delta G naught is called the standard Gibbs energy change of reactions. Okay. Okay. So this delta G standard change of reactions. Okay, right? So, and again, for fugacity again, as in the previous lecture, we can vary that, you know, uh, the molar properties, right? Delta M naught equal to nu I M I naught, okay, right? So, we can apply this, okay, right? So, you can read it more. Okay, right? And then we apply it again to previous equations. Like for example, enthalpy here as standard condition. Remember here, notice standard condition and species I. Apply this equation here, and then we multiply with stoichiometric coefficients here, over here, and then in the definitions that we can see that, right? See that here division of 4, 14, and 13.12. 13.12. 13.12 like here. Delta G naught summation of I V I G I naught. Okay, so we can apply it also here, right? So we apply it here, then we got it there. Okay, right? See this delta enthalpy naught, and this value here, it become delta G naught. Okay. Okay, right? So we can rearrange it again to this form here, delta, the differential of delta G naught RT over dt equal to minus delta H over RT square. Or we can rewrite it into this form. Okay, right? Okay, so if we look at this equation here, it gives the effect of temperature on the equilibrium constants and hence on the equilibrium conversion if delta H naught is negative, right? This is negative, right? Then is this negative if the reaction is an exothermic? Okay, why delta H is negative? Remember, H equal to U plus PV, right? So when it exothermic, what exothermic means? It release heat. So H equal to U plus PV, the U reduce. So the final H will be smaller. So that's why delta H is negative because higher, smaller final. So this negative. But okay, so when it's isothermic, the equilibrium constant decreases as the temperature increases. Okay, so what does it mean here? Okay, if let's say this is negative, right? When you further decrease the temperature, what will happen? Decrease the temperature. Ah, decrease the temperature. Okay, let's go back again. If this is negative and then we increase the temperature, what will happen? This value will become very big, isn't it? When they're very big and they become negative, this becomes smaller. Right? So it's opposite if it's the endothermic. So endothermic H equal to U plus PV. Endothermic, it's cold, so absorb heat. So U increase. Right? So the delta H will be positive. So when the endothermic delta H is positive, temperature in, increase. Okay, this is positive, positive, right? So because it's double, okay, right? Delta is positive and then it's positive, but ln here, this become very small, then K should be increased. Remember, ln graph K, like this, isn't it? So this is the axis, this y-axis, right here. Right, the smaller the value, the bigger it is. So it go this way, right? Okay, so if delta S, the enthalpy change of heat transfer is assumed to be dependent of T, integration from equation this, and particular temperature T prime to arbitrary temperature T leads to the simple results like this. Okay, this is a temperature difference. Okay, so this separate question implies that a plot of K plus reciprocal absolute temperature is a straight line. Okay, so we will get a straight line like in figure 13.2. Okay, later we will see the graph here. Okay, so we got all these straight lines here. Okay, some of the line is increased, some of the line is decreased because some of the reaction is exothermic, some are endothermic. Okay, right? So that's why some are increased, some are decreased. Okay, right? Okay. Okay. For rigorous development, the effect of temperature and equilibrium, we also can define Gibbs energy into G naught I equal to H I naught minus T entropy naught. Okay, right? And then we can sum it all over again here. Okay, right? We manipulate. Okay, right? So toward the end, right? We can get this equation here, right? And then we for delta S here, we use this equation here. Oh, I'm sorry, not delta S. For the enthalpy, right? And delta enthalpy naught is delta enthalpy extended condition plus the this, right? R time specific heat at constant pressure, right? And the change of temperature here. So I think we have done this previously, right? In previous lecture. For this is from in chapter 4, right? Okay, right? So the temperature here, we apply for the entropy here, and then we will get this equation here. Okay, right? So you guys can go back and see and think how does it apply. Okay, right? Okay. Okay, and then become more complicated here. Okay, right? And delta S, we know that this, right? Because we know that Gibbs energy is equal to, delta H equal to Gibbs energy plus Ts, right? Okay, hence we manipulate it around, so we got this equation here, and then we become so complicated. Okay, right? So we got this equation here. G is a delta and H naught at standard condition. Well, at the initial. Okay, this is at the initial. in all of this question here. So it will be very difficult to calculate. So what you can do, you can use the equation at the backs of the books, right? It tell you how to calculate this by discretize it into simpler equation. Okay, I'm not sure. I think we have done this before. I did ask you to program it, right? So you can go back to the appendix and how to doing it. Okay, so it's very easy. Right? We just program it in Excel and we'll give you the answer. Okay, right? The equilibrium constant also can be in another form. Okay, right? So we can write it into K naught, K1, and K2. Okay, what is K naught? K naught, the first factor cannot represent the equilibrium constant at reference temperature. Okay, right? Remember, I told you in thermodynamics, we don't care how we measure it. Okay, what is your datum? What's more important is that what is the difference before and after, isn't it? Okay. So there's a K naught can be in terms of exponent, this value here. And K1 is a multiplier that supplies the major effect of temperature, such as the product of KO, K0, K9. So we can use this equation here. And K2 account for much smaller temperature influence resulting from change of delta S with the temperature. So we can use this equation here. Okay, right? With the heat capacity, we can use the equation here. All right. So it become more complicated. Okay, right? Evaluation of equilibrium constant. Okay, this, right? So I will skip this. Okay, right? For standard conditions for gas, the ideal gas state, a pure gas at standard state pressure P naught at 1 bar, we can write it into, we find that the viscosity Y naught is equal to P naught, right? And then for the gas reactions, this is in the solution to the reference, the solution to the pressure. Right? So we can rewrite it into this form. Okay, right? So K equal to the sum of this, right? At nu I. Okay, since that the equilibrium constant K is a function of temperature only, but it relates to the viscosity reacting to species as they exist in the real equilibrium mixture. Okay, right? So as you remember that viscosity can be written into this form here, right? In the solution, remember, you set up a cap there, that's the solution. Phi, then what is phi? Remember, viscosity coefficients, Yi, P, and then we can rewrite it into this form. Okay. Okay, right. So okay, if we assume that the equilibrium mixture is an ideal solution, then the phi, right? The phi here, right? Phi here, right? For the solution should equal to the phi for that species, right? For that species, right? This in the solution, so it should be the same. Okay, right? So we can rewrite this equation here, except that it's not in the solution form anymore. Okay, right? So this is the procedure, right? I'm sorry, it's not the procedure, it's the conclusions, okay, right? So the conclusions of this equation here for ideal gas reactions. I think you guys can read it, okay, right? So basically, it is all that what we have assumed, okay? What I already explained earlier, okay, right? So this is kind of like to conclude that. Okay? Okay, for reaction occurring in liquid phase, okay, right? For liquid phase, remember liquid phase is different. We have this solution here and not, okay, right? For usual standard state for liquid, the viscosity of liquid I and temperature of the system at 1 bar. Okay, right? So we have done this before, right? So this is the gamma, right? Gamma is the activity coefficients. Remember, for phi, that is for vapor. Gamma is the activity coefficient, that's for liquid. Okay, right? So we can manipulate around, we got this equation here. Okay, right? So for this liquid in liquid form, we can use this. Okay, right? We can use this equation here. Right? Except for high pressure, the exponent term is close to unity and may be omitted. What does it mean? Means that when exp p minus p naught, okay, when pressure is very high, what will happen here? This become a negative value, isn't it? So E become a negative value. So a negative value, E power negative value. So this become almost toward 0, right? So 0, so E power of 0, then 1, right? Because it's 1 power 0 is 1, right? Okay, so that the equilibrium mixture, the ideal solution, uh, uh, gamma here is unity. Then we can write, okay, for ideal solution. Remember, ideal solution, the gamma here will be equal to 1. So we will cancel that and then we get this equation. Okay, this is a simple relation known as the law of mass actions. Yeah, because liquid often form non-ideal solutions. Okay, yeah, liquid it does not behave like an ideal solution. But for to make our calculation easier, then normally we assume it to be ideal solutions. Okay. Okay, right. So this is for the fugacity for solution. Okay, in KIMI. Okay, right. So this statement here just to indicate that, okay, right, uh, as the composition is toward infinite dilution, then it will behave more like a Henry's law. So, right. So if you remember Henry's law, right, which is YIP equal to XIH. Okay, right. So it's very similar here. Okay, right. So means that if you plotted there, phi and molality, so at a very final dilution here, it very much follow Henry's law. Okay, right? So if is it at pure species, then it will follow Lewis Randall's. Right? Okay, for standard fugacity, which is the knob here, I think you guys can look at it, right? We can compare it here. Okay, not standard to the actual, and we got the ratio here as M, Mi. Okay, equilibrium's conversion for single reactions. Okay, right? Let's say we have it here, and for single reaction, we have A in gas form and B in liquid form to produce C in aqueous form. Okay, that may be a mixture of two. Okay, right. So for in case of delta G, value is mixed standard state C as a solute in ideal 1 molar aqueous solution, B as pure liquid at 1 bar, and A as a pure ideal gas at 1 bar. For this chart of standard states, the equilibrium constant is given by this. Okay, okay, so this is for the product C here. Okay, right? And then this is the fugacity there. Okay, right? The ratio. Okay, right? And this is M1. And then for B here, because it is in pure liquid form, then we use gamma. Right? And then the liquid fraction. Okay, and then A is a pure ideal gas. Then we use fugacity and the pressure standard condition, and it should equal to K. Okay. Okay, and next will be the phase rule. Okay, right. Let's continue. Okay. Next will be the phase rule and Durham's theorems for reacting system. Okay, as you guys have done earlier for non-reacting system or the freedoms, right? Degree of freedoms can be denoted by this equation here, where 2 minus pi and n. Pi is the number of phases, n is the number of species. Right? But somehow, when you have a reacting system which have more than one reactions, then we should add R. Okay, right? What is R? R are independent chemical reactions at equilibrium within the system. So then there is a total of pi minus 1 n plus r. Okay, right? So we have this equation here, and then we can simplify that. So we have a very much similar equation except minus r. Okay, right? R is independent chemical reaction at equilibrium between the system. Okay, right? So the Onui-Rami problem application to determine number of independent chemical reaction is done systematically as follow. Write the chemical equation for the formation, constituent and else. Combine this equation and the element not considered present in the elements. Okay, right? So that will be in the example. Yeah, I think for this you can go to example 13.11 or the SI attached. Okay, right? Okay. Another form, okay, right, that we need to add is, you can see the equation here is the letter S. Okay, why is that letter S? Letter S is the special constraint maybe placed on the system that allow additional equation to be written over and above those considered in developments of 13.6. Okay, right? So if we have this equation here, but maybe we have some other constraint. Okay, right? So we can use this equation here. Okay. Okay, right. So there will be also example on that. You guys can look at it. Okay, in the examples. Okay, multi-reactions equilibria. Okay, multi-reaction equilibria. Sometimes in the reaction there are few reactions occur at the same time. Okay, so how we handle that? Okay, we denote it as, okay, in addition, a separate equilibrium constant is evaluated for each reaction J. Okay, right? So we have a J here. Okay, right? So when the constant J varies the I, right? Or the pi here, I don't know how to call it here. The sum products of these should equal to Kj. Or we can write Kj in this form here, which is very much similar to the previous equation that we know, except the addition of J. Okay, right? Okay, and also we can rewrite it, the total Gibbs energy, into this form here, N1, N2, N3. Okay, right? So this will tell you what is the procedure. Right? Need to evaluate the system. You guys can read this procedure here. Right? Just basically just mathematics. All right? So you need to apply Lagrange multiplier, lambda k, and so on. Right? Okay, so I will not much focus on this. You guys can read it and from the notes also. Okay, right? Very much interested to introduce you the fuel cell. Okay, right? So what is a fuel cell? I think some of you know what a fuel cell is. Fuel cell is behave like a battery, but it's due to the chemical reaction in exchange of the electron. Okay, right? So we can read it here. A fuel cell similar in some aspect to an electrolytic cell or battery. Is a device in which a fuel is oxidized electrochemically to produce electric power. Okay, that so for a hydrogen fuel cells, you have a hydrogen gas here split into two hydrogen atoms to produce two electrons. And on the cathode, the oxygen, right? It react with two electron, react with the two hydrogen to produce water. Okay, so you guys can see here, that's why people like fuel cell, because it seems that here it does not pollute the environment, it just produces water. But somehow the fuel cell itself, it have some chemical to produce it. That's still to be an issue. Okay, before we go further, okay, this for uh, acidic, right? For acidic, and this for the alkaline, okay, right? Reaction, half reaction, H2 plus 2 hydroxide to produce water and electron, and then this electron here will oxidize the oxygen and water to produce the hydroxide here. So toward the end, the main product is just water. Okay, this technology is not new. Have been in the been developed since, I think, since the 50s or 60s, I think. But there's a People think it's promising in the 70s, but somehow, even though it's clean, it's very difficult, okay, to produce hydrogens. Okay, right? Even though hydrogen is a clean fuel, but the process to produce hydrogen is expensive. I mean, in Sarawak here, the state government is really keen to use the hydrogen because we produce the hydrogens from, not from electrolysis of water. That's very expensive. They produce hydrogen from natural gas. Okay, right? The cracking of reaction, or they call it cracking, right? Cut the natural gas, most possibly methane, and turn it into hydrogen. Okay, right? So, okay, so this is what happened in the fuel cell. So we have the electrolyte, which normally we have a membrane, this is the main hindrance of the technology, the membrane there, okay, right? Because it's been patented, and people try to produce a very cheap membrane, but still I don't think they're still successful. Okay, that's another reason why fuel cell is not widely used. And number one is just now, right? The fuel, right? The hydrogen is expensive to be produced. It's also expensive to be stored. Okay, right? If you notice that, if a helium balloon, okay, right, you tie it in a balloon, tomorrow morning it will not float anymore. That's for helium. With hydrogen, it's even smaller. Yeah, so very difficult to store and produce it. Number one. Number two is the membrane used for fuel cell. And number three is that the lifespan of fuel cell. Okay, right? The membrane have the lifespan, and also within the membrane, they need some chemical also for it to work, right? Acidic or alkaline. Okay, right? Aqueous for it to work. And then, and this process cause it to be quite expensive. Okay, right? So that's why it's not very common nowadays. Okay, but somehow, okay, this is show you how we can calculate the heat or power, right, from the fuel cell, right? So delta H equal to Q plus work by the electric here. Okay, Q, the heat produced is T delta S, easy, right? The temperature is constant. And then delta H can be calculated using this equation. You can plus this Q, plus it with T delta S, and work by the electricity. Okay, right? Or for reversible cell, you can find the work for the electricity can be calculated using this, which is equal to delta G. Okay. And then we can further calculate that, okay, by using Q. Okay. Q is the two number of Avogadro number, and E is the charge of each electron in column, right? So we can rewrite it into Q equal to minus 2F. Okay, F is the Faraday constant, and then time E. E is the voltage. So we got for the voltage here, EMF, right? We from this equation here. Right? For any battery, the most important is the voltage, right? The bigger the voltage, the more power you can extract. Okay, right? And this is the example of calculations, right? How we can calculate the electrical potential for the fuel cell. Okay, so you can go through it. If you don't understand, come and talk to me. Okay, right? And the fuel cell also we can calculate using this equation here, IDCPH, okay, right? At the end of the books in the appendix. You can go and have a look at it. Okay, right? Try to program in your Excel, very easy. We have done it last semester before the MCO, right? And then, and also fuel cell also, apart from hydrogen, people also have developed fuel cell that can work on methanol. And again, in methanol, still expensive. Okay, right? You need to react methane with water, right, or steam to produce methanol. So that is also another expensive fuels. And also, it also require a special membrane. Okay, right? Okay, right. So in this case here for the methanol, okay, right, for this equation here, it react with water to produce hydrogen, electron, and carbon dioxide. Okay, so we don't like carbon dioxide, isn't it? Right. So this is greenhouse gases, right? So the hydrogen, for me, hydrogen is still the best part. To produce hydrogen is expensive. Okay, that's it for today lecture. Okay, now please read the books, right? Okay, for my old books, it's the 7 editions. It is chapter 13, or you can read also Richard Elliot and Lyra. Okay, chapter 14 on reacting system. Okay, so if you have any questions, feel free to contact me, and all the best, and hope to see you again. Okay, so bye bye.